Hello, friend. Welcome to another quiet journey through the cosmos. Tonight, close your eyes for just a moment. Picture a single speck of light, smaller than an atom, weightless, timeless. Now, imagine that speck has been traveling for 13.8 billion years just to reach you right here, right now. Every photon that touches your skin, that warms your face, that lets you see these words, carries a story older than planets, older than stars, older than time itself. What if I told you that the light resting gently on your eyelids began its journey before anything you know existed? Before we drift into this ancient story together, if you find peace in these cosmic whispers, you might like to stay a while. You can gently tap the like button, subscribe, if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's begin. Some nights when the world feels too loud, it helps to remember that we are always bathed in ancient light. Right now, photons that left the sun 8 minutes ago are landing on your skin. But others, the ones from distant stars, have been traveling for thousands, millions, even billions of years. Each one a messenger from a time before humans, before Earth, before anything we call familiar. Tonight we follow one photon, born in the first breath of the universe through every transformation, every collision, every silent crossing of the void until it arrives here in this moment, completing a journey almost too vast to comprehend. Scientists suggest that in the very first fraction of a second after the Big Bang, something extraordinary happened. The universe, unimaginably hot and dense, burst into existence. Not exploding into space, but space itself, expanding, carrying energy with it. In that primordial fire, temperatures soared beyond 1 trillion degrees. Matter, as we know, it couldn't exist yet. There were no atoms, no molecules, just a seething ocean of quarks, gluons, and pure energy. And in that chaos, photons were born, countless trillions of them flooding the infant cosmos with light. But here's something beautiful and strange. Those first photons couldn't travel, not yet. The universe was too thick, too crowded. Imagine trying to walk through a room so packed with people that every step forward pushes you into someone else. That's what it was like for light in those early moments. Every photon born from the intense energy of creation would travel only a tiny distance before colliding with an electron or a quark scattering in a new direction, trapped in an endless dance. The universe was luminous, yes, but it was also opaque, a glowing fog with no way through. This era, scientists call it the Photon epoch, lasted for about 380,000 years. In cosmic terms, that's a heartbeat. But for a photon trying to escape, it must have felt eternal. Research shows that during this time, the universe was cooling, expanding, stretching like bread dough in an oven. As it grew, the temperature dropped, and slowly, conditions began to change. Then came a moment that would transform everything. The temperature fell to about 3,000 degrees Kelvin, cool enough for something miraculous. Electrons, which had been zipping around freely, finally slowed down enough to be captured by protons. They combined, forming the very first hydrogen atoms. This process, called recombination, was the universe's first great letting go. Suddenly, photons had space to move. The fog lifted. Light, for the first time, could travel freely across the cosmos. Imagine that moment. After hundreds of thousands of years of being trapped, bouncing endlessly in the thick plasma light, was suddenly free. It streamed outward in all directions, carrying with it the image of the universe as it was in that instant. Scientists call this the cosmic microwave background, or CMB. It's the oldest light we can see. And here's the wonder of it, we can still detect it today. When you tune an old television to static, about 1% of that snow on the screen is actually the afterglow of the Big Bang ancient photons that have been traveling for over 13 billion years, now arriving as faint whispers of microwave radiation. Our photon, the one we're following tonight, was born in those first moments. It emerged from the fire scattered 1 million times And then when the universe finally cleared, it began its true journey. But where would it go? In those early days, there was no destination, no sun to orbit, no Earth to land upon, just darkness and hydrogen and the silent pull of gravity slowly drawing matter together. Some people think of the Big Bang as an explosion, a firecracker going off in empty space. But that's not quite right. It wasn't an explosion in space. It was the explosion of space itself. Every point in the universe was the center. Every photon, no matter where it traveled, was moving away from every other photon carried by the expansion. Even today, that expansion continues. The universe is still stretching, still growing, and the light from those earliest moments is still reaching us, cooled and redshifted, a gentle reminder of how far we've come. There's a question that often arises when people learn about the Big Bang. If the universe is 13.8 billion years old, and light has been traveling all that time, why can't we see the edge? Why can't we look out and see the beginning? The answer is both simple and profound. We can. Every time we look at the cosmic microwave background, we are seeing the edge not of space, but of time. We're looking back to the moment when light was first set free. Beyond that, there is no before that we can see. The universe was opaque. It's like trying to see through a wall of fog. The light simply couldn't reach us from any earlier. But let's return to our photon. Newly freed, it travels outward. The universe around it is still simple. Hydrogen, helium, a trace of lithium and darkness, no stars yet, no galaxies. Just the faint glow of the CMB slowly fading as the universe expands and cools. This is the moment when our photon begins its voyage across time, a voyage that will take it through the birth of stars, the formation of planets, and eventually to you. What's remarkable is that photons don't age, they don't decay. A photon born 13.8 billion years ago is in a sense the same age now as it was then. From its perspective, if we could imagine such a thing, no time passes at all. Einstein's theory of relativity tells us that at the speed of light, time stops. A photon exists in a kind of eternal now, experiencing its entire journey from creation to absorption in a single timeless instant. It's only we, the observers, moving slower, bound by mass and gravity, who perceive the passage of billions of years. This is one of the quiet miracles of the cosmos. Light doesn't wait, it doesn't pause, it simply is. And yet, because of the vast distances involved, that light becomes a time machine. When we look at a star 10 light years away, we see it as it was 10 years ago. When we observe a galaxy millions of light years distant, we witness its past. And when we detect the cosmic microwave background, we are seeing the universe as it was 380,000 years after the beginning. Every photon is a fossil, a record of the moment it was born. Have you ever wondered what it would be like to live in that early universe? To float in the warm glow of the CMB, surrounded by pure hydrogen waiting for the first stars to ignite? It would be a universe without color, without shadow. Just a soft, even light in every direction, slowly dimming as space itself stretches. Some researchers suggest it would feel like being inside a cosmic oven, the temperature dropping degree by degree, year by year, waiting for anything to happen. And then, after millions of years of waiting, it did. Gravity, patient and relentless, began to pull hydrogen together. Small clumps formed then larger ones. The gas clouds grew denser, hotter. And in the hearts of these collapsing clouds, something astonishing occurred. The pressure and temperature rose so high that hydrogen atoms began to fuse, releasing tremendous energy. The first stars ignited. The universe, dark for so long, began to glow again. But this time, the light was different. Not the uniform glow of the CMB, but the brilliant, focused fire of fusion. Stars scattered across the darkness like sparks in a night sky. Our photon drifting through space would have witnessed this transformation. The dark ages ending, the cosmic dawn beginning. And in time, some of those stars would die, scattering heavier elements, carbon, oxygen, iron, into space. Those elements would gather, forming new stars, new planets. One of those stars would become our sun, one of those planets Earth. But we're getting ahead of ourselves. Before our photon could reach this world, before it could touch your skin and complete its journey, it had to travel through unimaginable distances, through eras of darkness and eras of light, waiting for the universe to become the place where you could exist. Right now, as you listen, photons are landing on you from every direction. Some are 8 minutes old, fresh from the sun. Others are years old from nearby stars. A few are thousands, even millions of years old from distant galaxies. And among them, perhaps, are photons from the very edge of the observable universe, carrying the faint echo of creation itself. You are always held in ancient light. You are never alone in this darkness. The journey of a photon is the journey of the universe itself, from fire to form, from chaos to beauty, from the beginning to this breath, this heartbeat, this now. And our photon story has only just begun. It has crossed the threshold. It has witnessed the birth of stars, but it hasn't yet found its home. Not yet. For that, it must travel further, through voids and clouds, through centuries and silence, until at last it finds the sun, and then, perhaps you. Picture this. You're holding a flashlight in the thickest fog you've ever seen. You press the button. Light floods out, but it doesn't reach far. Just a few inches, maybe a foot, before the fog swallows it completely. Now imagine that fog is the entire universe stretching in every direction, and you are a photon trying to escape. That was the reality for the first 380,000 years of existence. Light was everywhere, but it couldn't go anywhere. The universe in those earliest moments wasn't just hot, it was unimaginably dense. Scientists estimate that shortly after the Big Bang, temperatures reached about 10 billion degrees Kelvin. At that temperature, atoms, as we know them, simply cannot exist. Instead, the cosmos was filled with what physicists call a plasma, a roiling sea of subatomic particles, protons, neutrons, electrons, all moving at incredible speeds, smashing into each other again and again. And scattered throughout this chaos were photons, trillions upon trillions of them, born from the energy of creation itself. But here's the strange part. Even though the universe was glowing radiant with light, it was also completely opaque. You couldn't have seen through it, not even for a moment. Every photon that tried to move forward would immediately collide with a free electron, scatter in a random direction, then collide again and again and again. Imagine being in a crowded room where every step you take pushes you into someone else, spinning you around, sending you off in a new direction. That's what it was like for light, a cosmic traffic jam with no way out. This era is sometimes called the Photon Epoch, and it's one of the most misunderstood periods in cosmic history. Many people assume that because there was light, the universe must have been bright clear, something you could see through like looking up at a sunny sky. But research shows the opposite. The early universe would have been more like being inside a star surrounded by energy. Yes, but unable to see anything beyond the glowing haze immediately around you. Light existed, but vision, the ability to look across distance and perceive form, did not. Our photon, the one we've been following, was born into this. Released from some nuclear reaction in the primordial soup, it shot forward at the speed of light, only to crash into an electron a fraction of a second later. The collision sent it spinning off in a new direction. Then another collision. Then another. Scientists call this process Thomson scattering, and it happened constantly. Every photon in the universe was trapped in this endless pinball game, bouncing between particles unable to travel more than a tiny fraction of a millimeter before being deflected again. To understand just how trapped light was, consider this. In a single second, a photon moving unobstructed through empty space can travel about 300,000 kilometers, roughly the distance from the Earth to the Moon. But in the dense plasma of the early universe, that same photon might only manage to travel a few centimeters in the same amount of time because it's constantly being scattered. Some estimates suggest it would take a photon thousands of years to cross what we would now consider a short distance, simply because it kept getting knocked off course. And yet, the universe was expanding. Even as photons bounced helplessly between particles, space itself was growing, stretching, cooling. This is one of the key insights of modern cosmology. The universe doesn't expand into something. There's no edge, no boundary. Instead, the fabric of space itself stretches, and everything within it, galaxies, stars, particles, photons, gets carried along. As the universe expanded, the average distance between particles increased. The density dropped, the temperature fell, and slowly conditions began to shift. For hundreds of thousands of years, nothing fundamentally changed. The universe remained a glowing fog, opaque and chaotic. But around the 380,000-year mark, something extraordinary happened. The temperature cooled to about 3,000 degrees Kelvin. That might still sound incredibly hot, and it is by human standards, but in cosmic terms, it was a critical threshold. At that temperature, electrons which had been zipping around freely finally slowed down enough to be captured by protons. They combined, forming the first stable hydrogen atoms in the universe. This process, called recombination, is one of the most important events in cosmic history. It's a bit of a misleading name, actually, because it wasn't a recombination at all. The electrons and protons had never been combined before, but the term stuck. What matters is what happened next. Once electrons were bound inside atoms, they were no longer free to scatter photons. The universe, which had been opaque for hundreds of thousands of years, suddenly became transparent. Light could finally travel. Imagine that moment. The fog lifts. For the first time since the Big Bang, photons can move freely across vast distances without being deflected. They stream outward in all directions, carrying with them an image of the universe as it was at that exact instant. This light, the afterglow of recombination, is what we now call the cosmic microwave background. It's the oldest light in the universe, and we can still detect it today, cooled and stretched by billions of years of expansion, arriving now as faint microwave radiation. Our photon, freed at last, began its journey in earnest. No more collisions, no more scattering, just open space and the long, patient drift across the cosmos. But here's something scientists find deeply fascinating. The cosmic microwave background isn't perfectly uniform. There are tiny variations in temperature fluctuations of only a few millionths of a degree, but those tiny ripples are incredibly important. They represent the seeds of all structure in the universe. Regions that were slightly denser than average would go on to form galaxies, stars, planets. Regions that were slightly less dense would become the vast voids between galaxies. When astronomers first measured the CMB in detail, using satellites like COBE, WMAP, and Planck, they found those fluctuations and realized they were looking at a cosmic blueprint. The map of the cosmic microwave background is in a sense a baby picture of the universe, showing the patterns that would eventually grow into everything we see today. Every galaxy, every star, every planet, including Earth, can trace its origin back to those tiny ripples in the primordial light. But let's think about what this means for our photon. When it was released during recombination, the universe was about 1,000 times smaller than it is now. The wavelength of our photon, initially in the visible range, has been stretched by the expansion of space. What was once a photon of visible light is now a microwave, its energy diluted, its wavelength extended. This process, called cosmological redshift, is how we know the universe is expanding. The further away something is, the more its light has been stretched, and the redder, or in this case, the longer in wavelength it appears. There's a common misconception that the cosmic microwave background is leftover heat from the Big Bang. That's not quite right. It's leftover light. The photons themselves haven't changed. They're the same particles that were released during recombination. What's changed is the space they're traveling through. As the universe expands, the wavelengths stretch. And what was once a hot, bright glow has cooled into a faint whisper. Some people wonder if the CMB is all around us. Why don't we see it? Why isn't the sky glowing? The answer is that we do see it, just not with our eyes. Our eyes are sensitive to visible light wavelengths between about 400 and 700 nanometers. The CMB, after billions of years of redshift, now peaks at a wavelength of about 1 millimeter, firmly in the microwave range. To detect it, we need special instruments, radio telescopes, and satellites designed to pick up those faint microwave signals. But it's there always surrounding us, a constant hum of ancient light. Here's something beautiful to consider. Every cubic centimeter of space contains about 400 photons from the cosmic microwave background. Right now, as you sit here, you're immersed in this sea of ancient light. You can't see it, you can't feel it, but it's there passing through you, carrying information from a time before, stars, before galaxies, before anything solid existed. In a very real sense, we are always bathed in the afterglow of creation. Research also shows that the CMB is remarkably uniform. No matter which direction we look, the temperature is almost exactly the same, about 2.7 Kelvin above absolute zero. This uniformity was puzzling at first. How could regions of space that are now billions of light years apart have almost identical temperatures if they were never in contact? The answer scientists believe lies in a brief period of exponential expansion called cosmic inflation, which occurred in the first fraction of a second after the Big Bang. During inflation, the universe grew by a factor of at least 10 to the power of 26, smoothing out any initial irregularities and setting the stage for the uniform CMB we observe today. But even with that uniformity, the tiny fluctuations remain. Those ripples imprinted in the CMB are like fingerprints of the early universe. By studying them, cosmologists can learn about the composition of the universe, the ratio of ordinary matter to dark matter, the amount of dark energy, even the curvature of space itself. The CMB is one of the most powerful tools we have for understanding the cosmos, a fossil record written in light. Our photon newly freed didn't know any of this. It simply traveled outward away from the dense regions where it was born into the expanding void. The universe around it was still simple. Hydrogen, helium, a trace of lithium, and darkness. No stars had formed yet, no galaxies. Just the faint glow of the CMB slowly fading as space stretched and cooled. This was the edge of the cosmic fog, the boundary between the opaque past and the transparent future. And as our photon crossed that boundary, it became part of the oldest light we can ever hope to see. What must it have been like to be there in that moment, to witness the lifting of the fog, the first clear view across the cosmos? Some researchers describe it as the universe opening its eyes for the first time, transitioning from a state of blindness to a state of sight. Before recombination information couldn't travel far. Light was trapped. Afterward, information could flow freely, allowing structure to form, complexity to emerge, and eventually consciousness to arise. It's humbling, isn't it? To know that the light we detect from the cosmic microwave background has been traveling for over 13 billion years, carrying a message from the earliest moments of existence. And it's still arriving, still delivering that message, still reminding us of where we came from. Every time we measure the CMB, we are in a sense listening to the universe's first words, the echoes of its birth cry. But the story doesn't end with recombination. Our photon and countless others like it were now free to wander, free to drift through the darkness that followed. And that darkness, as we'll see, was profound. For after the fog lifted, the universe entered a long, quiet night, an era with no stars, no light sources except the fading glow of the CMB. The cosmic dawn was still millions of years away, and in that silence and that vast emptiness, the universe waited, gathering itself, preparing for the next great transformation. After the light came, the longest night the universe has ever known. Imagine drifting through absolute darkness for not just hours, not just years, but for hundreds of millions of years. No stars to guide you, no galaxies to mark the distance. Just hydrogen helium, and the fading echo of creation slowly cooling into silence. This was the cosmic dark ages, and our photon traveled through every moment of it. When the fog of the early universe finally cleared, when recombination set light free to wander, you might think the cosmos would have been brilliant, radiant, full of new possibilities. But the opposite happened. The universe went dark. The cosmic microwave background, that ancient glow we spoke of, was fading, redshifting, cooling with every passing millennium. And nothing had yet ignited to replace it. No fusion reactions, no stellar fires, just cold gas spreading thinner and thinner across an ever-expanding void. It's one of the great ironies of cosmic history. The moment light was freed was also the moment darkness truly began. Scientists estimate this dark age lasted anywhere from 100 million to several hundred million years, depending on where you were in the universe. That's longer than the entire history of complex life on Earth. Longer than the age of the dinosaurs. Longer than the time between the first mammals and now. And during all of that, nothing burned, nothing shone. The universe was a vast, cold, empty cathedral waiting for its first candle to be lit. Our photon released during recombination found itself adrift in this emptiness. It had escaped the plasma prison, yes, but now it faced a different kind of isolation. There was nothing to interact with, no atoms dense enough to absorb it, no surfaces to reflect it. Just the slow, patient glide through space that stretched farther with every second. And as space expanded, the photon's wavelength stretched too, shifting from visible light into the infrared, then deeper into the microwave spectrum, losing energy, cooling, but never stopping, never slowing. Here's something most people don't realize about the dark ages. Even though there were no stars, the universe wasn't completely uniform. Gravity was already at work. Those tiny fluctuations we mentioned earlier, the ripples in the cosmic microwave background were growing. Regions that were slightly denser than average began pulling in more hydrogen. Regions that were less dense became even more sparse. Slowly and visibly, the universe was organizing itself into a web-like structure with dense filaments of gas stretching between vast, empty voids. Research shows that these filaments, sometimes called the cosmic web, are still the fundamental structure of the universe today. If you could zoom out far enough to see the entire observable cosmos, you'd see galaxies clustered along these filaments, like beads on a string with enormous voids in between, where almost nothing exists. That pattern was set during the dark ages, carved out by gravity, working patiently in the silence, shaping the raw material of creation into something that would eventually become stars, galaxies, and us. But back then, none of that was visible. You couldn't have seen the filaments forming. You couldn't have watched the gas clouds collapsing. There was no light to reveal any of it. The universe was like a sculpture being carved in a pitch-black room, with only gravity's invisible hands doing the work. And our photon traveling through this darkness was a witness to none of it. It simply moved, carried by the expansion, stretched by the passing eons, waiting for something, anything to happen. Then slowly something did. Deep within the densest clouds of hydrogen, where gravity had pulled gas together most tightly, the pressure began to build. Imagine a balloon being squeezed. The tighter you squeeze, the hotter the air inside becomes. The same principle applies to cosmic gas clouds. As gravity compressed them, the temperature at their centers started to rise. 1 million years passed, then 10 million, then 50 million, and still the cores of these clouds grew hotter, denser, more compressed. Scientists call these collapsing clouds protostellar clouds, the ancestors of stars. But they weren't stars yet, not even close. They were just pockets of gas warmer than their surroundings, but still far too cold to ignite fusion. The temperature needed for hydrogen fusion is about 10 million degrees Kelvin. These clouds were nowhere near that. They were maybe a few thousand degrees at most, but they were getting there, slowly, patiently. Gravity doesn't rush. What's fascinating is that We can't observe the Dark Ages directly. We can infer what happened based on simulations and indirect evidence, but there's no light from that era for us to see. The cosmic microwave background shows us the universe at 380,000 years old. The earliest galaxies we've detected with telescopes like the James Webb Space Telescope date to a few hundred million years after the Big Bang. In between, there's a gap, a blind spot in our cosmic vision. The Dark Ages are in a very real sense invisible to us. But we know they happened. We know because of what came after. When the first stars finally did ignite, they didn't appear randomly. They formed in specific places along those dense filaments we mentioned in regions where the Dark Ages had already done the work of gathering material. The darkness wasn't wasted time. It was preparation. It was the universe catching its breath, setting the stage for the brilliance that would follow. Our photon during this time would have been completely alone. Think about that for a moment. Traveling for hundreds of millions of years without encountering a single atom dense enough to notice it. No collisions, no interactions, just the endless drift through expanding space. Some physicists describe photons during the Dark Ages as fossils in flight, ancient particles, carrying information from a younger universe, but with no one and nothing to receive that information. Not yet. There's a question that often comes up when people learn about this era. If the universe was expanding and cooling, how did it ever get hot enough again to form stars? Shouldn't everything just keep getting colder forever? It's a good question. The answer lies in the difference between the temperature of space and the temperature inside collapsing gas clouds. Space itself was cooling, yes, but localized regions, places where gravity was concentrating matter, were heating up. It's like how the air in a room might be cold, but if you compress a small amount of that air quickly, it warms up. Gravity was doing the compressing, and over millions of years, that compression generated enough heat to spark fusion. The first stars, when they finally formed, were nothing like the sun. They were massive, hundreds of times the mass of our sun, burning incredibly hot and bright. Scientists call them population 3 stars, and not a single one of them exists today. They all died long ago, exploding as supernovae, scattering the first heavy elements into space. But in their brief lives, they transformed the universe. They ended the Dark Ages. They lit the cosmic dawn. Imagine being our photon drifting through darkness for 100 million years, and then suddenly in the distance a pinprick of light appears, then another, then 1,000 more. The universe, silent and black for so long, begins to glow again. But this time, the light is different. It's not the uniform glow of the cosmic microwave background. It's clustered, localized, fierce. It's the light of stars burning hydrogen into helium, releasing energy that floods out into the surrounding space. This transition from the Dark Ages to the cosmic dawn is sometimes called the epoch of reionization. Here's what that means. When the first stars ignited, their intense ultraviolet radiation began stripping electrons off the neutral hydrogen atoms that filled space. Remember, recombination, when electrons combined with protons to form neutral hydrogen reionization, was the reverse. The star's light was so energetic that it knocked those electrons loose again, turning the neutral hydrogen back into a plasma and ionized gas. This process took hundreds of millions of years to complete, gradually spreading outward from each new star until nearly all the hydrogen in the universe was ionized once more. Research shows that this epoch was patchy, uneven. Some regions reionized early wherever the first stars formed. Other regions remained neutral for much longer. The universe during this time would have looked mottled with bubbles of ionized gas expanding around each star cluster, slowly merging, gradually filling the voids. Our photon traveling through this changing landscape would have encountered pockets of ionized gas, then neutral gas, then ionized again, as the cosmic dawn spread unevenly across the heavens. But here's something beautiful. Even though the Dark Ages were dark to us, they weren't meaningless. During that long silence, the fundamental structure of the universe was being laid down. The cosmic web formed. The first proto-galaxies began to assemble. Dark matter, invisible and mysterious, was already pulling regular matter into its gravitational wells, creating the scaffolding that galaxies would later build upon. Without the Dark Ages, without that long period of quiet preparation, the universe we know today simply couldn't exist. Some scientists compare the Dark Ages to the gestation period before birth. Nothing seems to be happening on the outside, but inside everything is being assembled, organized, prepared. The universe was pregnant with stars during those hundreds of millions of years, and when they finally arrived, they arrived in force, transforming everything. Our photon continued its journey through this transition. By now, it had been traveling for hundreds of millions of years, its wavelength stretched far beyond the visible spectrum, its energy diluted by the expansion of space. It was no longer the bright, energetic particle it had been during recombination. It was older now, cooler, a relic of an earlier time. And yet it was still moving, still carrying information, still part of the great cosmic story. What's remarkable is how patient the universe is. Hundreds of millions of years is almost incomprehensible to us. Human civilizations rise and fall in mere thousands of years. The entire history of recorded human thought spans only a few millennia. But the universe measures time differently. It waits for gravity to do its work. It waits for clouds to collapse. It waits for temperatures to rise. And when the moment is finally right, when conditions align, it ignites. Not rushed, not hurried, just inevitable. The Dark Ages remind us that silence isn't emptiness. Darkness isn't absence. Sometimes the most important work happens when nothing seems to be happening at all. The universe was building itself during those long centuries, preparing for the light show that would follow. And when the first stars finally blazed to life, they didn't just illuminate the darkness. They transformed it, filled it with energy, and elements began the long process of creating the chemical complexity that would eventually lead to planets, to life, to consciousness. Our photon, ancient and patient, had witnessed it all: the fog, the clearing, the darkness. And now, finally, the first light. But its journey was far from over. Ahead lay billions more years, new encounters, new transformations. The universe was waking up, and our traveler would drift through every stage of that awakening, moving ever forward, ever onward, until at last, it would find a young yellow star in a quiet corner of a spiral galaxy and begin the final leg of a journey that started before time itself had meaning. The darkness was ending. The age of stars was beginning, and everything that would follow, from galaxies to planets to you, was about to unfold in ways the silent universe had been quietly preparing for all along. There's a place where light is born over and over again, dying and resurrecting in an endless cycle that can last for thousands of centuries. A place so dense that a single photon moving at the speed of light takes longer to escape than the entire span of human civilization. That place is the heart of a star, and our photon is about to enter it. The first stars ignited, the Dark Ages ended, and across the universe, in countless pockets of collapsing gas, fusion began. But what does that actually mean? What happens inside a star when hydrogen becomes helium, when matter converts to energy, when the universe learns to burn? Let's follow our photon into that fire and see what it means to be light in a place where light itself struggles to exist. Picture a ball of gas 1,000 times the mass of Jupiter, slowly contracting under its own gravity. As it shrinks, the core heats up. 1 million degrees, 5 million, 10 million. At around 10 million degrees Kelvin, something magical happens. Hydrogen nuclei, which are just single protons, begin moving so fast that when they collide, they overcome the electromagnetic force that normally pushes them apart. They fuse together, forming helium. And in that fusion, a tiny amount of mass disappears, converted into pure energy, according to Einstein's famous equation, E equals mc squared. That energy is released as gamma-ray photons, the most energetic form of light in the universe. This is where our photon is born, Not the same photon from the Big Bang, not the one that drifted through the dark ages, but a new photon fresh from a fusion reaction deep in the core of a young star. It emerges with tremendous energy, a wavelength measured in trillionths of a meter, carrying the heat of creation itself. And immediately it begins a journey that will take not seconds, not years, but potentially 100,000 years to complete. Because even though it's moving at the speed of light, the inside of a star is so unimaginably dense that it can barely move at all. Here's what happens. The gamma-ray photon shoots forward. Within a fraction of a millimeter, it collides with an atom, usually hydrogen or helium. The atom absorbs the photon, completely taking in all its energy. For a brief moment, the photon ceases to exist. Then almost instantly, the atom re-emits a photon, releasing that energy back into space. But here's the crucial part. The new photon doesn't necessarily go in the same direction. It shoots off randomly in any direction at all, and it's usually at a slightly lower energy, a slightly longer wavelength, because some of the original energy was absorbed as heat. Scientists call this process radiative diffusion, and it's one of the most important mechanisms in stellar physics. The photon takes one step forward, gets absorbed, gets re-emitted in a random direction, maybe backward, maybe sideways, maybe forward again. Then it takes another step, then another. Each step is tiny, just a fraction of a millimeter, and each step is random. It's like trying to walk out of a dense forest blindfolded, taking one step at a time, but you keep bumping into trees and changing direction. You'll eventually get out, but it's going to take a very, very long time. Research shows that a photon born in the core of a star like our Sun will undergo somewhere between 10 to the power of 24 and 10 to the power of 26 interactions before it finally reaches the surface. That's a 1 followed by 24 to 26 zeros. To put that in perspective, there are only about 10 to the power of 80 atoms in the entire observable universe. The number of times a single photon bounces around inside a star is incomprehensibly large, and each bounce changes it slightly, lowering its energy, stretching its wavelength, transforming it from a gamma ray to an X-ray to ultraviolet to visible light to infrared and sometimes back again. The core of a star is the densest, hottest region where fusion happens constantly. Temperatures can reach 15 million degrees Kelvin in a star like the Sun. The pressure is so intense that atoms are stripped of their electrons, existing as a plasma of bare nuclei and free particles. Our photon, freshly created, finds itself in this chaos, bouncing from nucleus to nucleus, absorbed and re-emitted millions upon millions of times. As it gradually works its way outward, the density decreases, the temperature drops. In the Sun, there's a region called the radiative zone, extending from the core to about 70% of the Sun's radius. In this zone, energy moves outward primarily through radiative diffusion, photons bouncing their way slowly toward the surface. The temperature here ranges from about 7 million degrees near the core to about 2 million degrees at the outer edge. It's still unimaginably hot, but it's cooler than the core, and the photons, though still scattered constantly, make slightly more progress with each interaction. Then, in stars like the Sun, there's another zone called the convective zone. Here, the plasma is cool enough and dense enough that radiation alone can't carry the energy efficiently. Instead, hot plasma rises, cools as it nears the surface, then sinks back down, creating massive convection currents. It's like water boiling in a pot, with bubbles of hot plasma rising and cooler plasma sinking. Our photon, trapped in this churning sea, continues to be absorbed and re-emitted. But now it's also being carried along by the motion of the plasma itself, sometimes rising, sometimes sinking, always bouncing. Scientists estimate that in the Sun, a photon takes about 100,000 to 170,000 years to travel from the core to the surface. Think about that. 100,000 years. The entire history of modern humans, from the first cave paintings to the present day, could fit into the time it takes a single photon to escape the sun. That's how dense a star is. That's how slow radiative diffusion can be. And yet, from the outside, the sun appears to shine steadily constantly. We don't see the individual photons struggling to escape. We see the average, the cumulative effect of trillions upon trillions of photons, all making their slow, random journeys outward. There's a common misconception that the light we see from the sun is somehow ancient, that we're seeing light from nuclear reactions that happened thousands or millions of years ago. That's not quite right. The photon that left the sun's surface 8 minutes ago and is now entering your eye is not the same photon that was created in the core 100,000 years ago. It's been absorbed and re-emitted so many times that its identity, if photons can be said to have, identity has been completely lost. What we're seeing is the energy from those ancient fusion reactions finally released, after being passed from photon to photon, atom to atom, slowly working its way to the surface. By the time our photon nears the surface, it has changed completely. What started as a high-energy gamma ray with a wavelength of a trillionth of a meter has been transformed into visible light with a wavelength of about 500 nanometers, the color we perceive as green or yellow. It has lost most of its original energy, dissipated as heat throughout the star, but it still carries enough to be seen to warm to sustain life on distant planets. The surface of a star. The photosphere is the layer from which photons can finally escape. It's not a solid surface like the ground beneath your feet, but rather a transition zone, a region where the gas becomes thin enough that photons can travel freely without being immediately absorbed. The temperature here on the sun's photosphere is about 5,700 degrees Kelvin cool compared to the core, but still hot enough to vaporize any known material instantly. And from this layer, photons stream outward in all directions, finally free after their long imprisonment. Our photon reaches the photosphere. It takes one last step, and suddenly nothing blocks it. No more atoms to collide with, no more absorption and re-emission, just open space stretching out in all directions. It has escaped. After 100,000 years of wandering through the interior, bouncing endlessly changing form countless times, it is finally truly free. And it begins to move not randomly, not in zigzags, but in a straight line at the speed of light heading out into the solar system. But here's something beautiful and strange. From the photon's perspective, if we can imagine such a thing, no time passes at all. According to Einstein's theory of relativity, time dilation means that at the speed of light, time essentially stops. For the photon, the moment it is created and the moment it is absorbed are the same instant. It experiences no duration, no passage, no journey. It simply exists in a timeless now. It's only for us, the observers bound by mass and moving slower than light, that the photon's journey takes time. For the photon itself, the 100,000 years inside the star, the 8 minutes crossing space to Earth, the billions of years traveling from distant galaxies, all of it happens in zero time. It's born and dies in the same eternal moment. This is one of the deep mysteries of light. Photons are in a sense outside of time. They don't age, they don't decay. A photon created at the Big Bang is from its own frame of reference the same age as a photon created 1 second ago. Time is something that happens to massive particles, to atoms and molecules and living things, but not to light. Light simply is eternal and unchanging even as it travels across billions of years of cosmic history. Inside, the star fusion continues. Every second, the sun converts about 600 million tons of hydrogen into helium. That's the mass of a small mountain transformed into energy released as photons every single second. And yet, the sun has been doing this for about 4.6 billion years, and it has enough hydrogen left to continue for another 5 billion years or more. Stars are patient engines burning slowly, steadily, converting matter to light with an efficiency that no human technology can match. different stars burn differently. Massive stars, those with 10, 50, or even 100 times the mass of the sun, burn much hotter and faster. Their cores reach higher temperatures, fusing not just hydrogen into helium, but helium into carbon-carbon, into oxygen, oxygen into silicon-silicon, into iron. Each stage releases energy, creating photons that must fight their way to the surface through even denser, even hotter material. These massive stars live fast and die young, burning through their fuel in just a few million years before exploding as supernovae. The photons created in their cores may never escape at all, trapped in the star until the moment of its violent death. Smaller stars, red dwarfs, with only a fraction of the sun's mass, burn cooler and slower. Their cores are less hot, their fusion rates are lower, and they can live for trillions of years, far longer than the current age of the universe. The photons they create may take even longer to escape, wandering through the dense interior for millions of years before finally reaching the surface and streaming out as dim red light. Our photon, born in a star somewhere in the universe billions of years ago, has completed its journey through the stellar interior. It has been transformed, scattered, absorbed, and re-emitted countless times. It has aged. The star helped sustain the fusion process, contributed to the pressure that holds the star up against gravity's pull. And now it is free, racing through space at 300,000 kilometers per second, heading toward an unknown destination. Maybe it will travel for billions of years, crossing intergalactic voids, never encountering anything. Or maybe it will find a small blue planet orbiting a quiet yellow star, enter an atmosphere, scatter through air molecules, and land gently in someone's eye, completing a journey that began in fire and ends in sight. The star continues to burn. New photons are born every instant. And the cycle goes on, light emerging from fusion, struggling through density, finally breaking free, carrying energy outward into the cosmos, illuminating the darkness, one photon at a time. 8 minutes and 20 seconds, that's all it takes for light to travel from the surface of the sun to your eyes. But in those 8 minutes, something extraordinary happens. A photon crosses 93 million miles of absolute emptiness, never slowing, never stopping, experiencing no time at all. While for us watching from Earth, those 8 minutes contain the entire gap between now and the light we see. What does it mean to travel when time itself doesn't exist for you? Our photon has escaped the sun. After 100,000 years of struggle through the stellar interior, it finally broke free from the photosphere and began its journey across space. But this journey is different from anything that came before. No more collisions, no more scattering, just pure unobstructed speed, straight and true, heading outward into the solar system. And in 8 minutes and 20 seconds, it will cross a distance so vast that it would take a commercial airliner flying at top speed more than 17 years to cover. Let's pause for a moment and consider what empty space really means. When we say the photon travels through a vacuum, we mean there's almost nothing there. Not air, not dust, not even stray atoms, at least not in any meaningful density. The space between the sun and Earth contains on average about 5 particles per cubic centimeter. That sounds like a lot until you realize that the air you're breathing right now contains about 25 quintillion particles per cubic centimeter. That's 25 followed by 18 zeros. In comparison, space is almost perfectly empty. So our photon racing outward at exactly 299,792,458 meters per second, the speed of light in a vacuum encounters essentially nothing. No resistance, no friction, no obstacles. It simply moves carried by its own nature, following the straightest possible path through the curved space-time around the sun. And here's the beautiful part. It doesn't slow down. It doesn't speed up. Light in a vacuum always travels at exactly the same speed, unchanging, absolute, the one constant in the universe where almost everything else is relative. Einstein's special theory of relativity tells us something profound about this speed. Light doesn't just happen to travel at 299,792,458 meters per second. That speed is woven into the fabric of reality itself. It's the maximum speed at which cause and effect can propagate the cosmic speed limit, the rate at which information can travel through space. Nothing with mass can reach this speed. Only massless particles, photons, and perhaps others can travel at light speed, and for them, it's not a choice. It's simply what they do. But here's where it gets strange. From our perspective here on Earth, the photon takes 8 minutes and 20 seconds to reach us. We can measure that time. We can watch the sun knowing that if it suddenly went dark, we'd continue to see it shining for another 8 minutes and 20 seconds before the darkness arrived. That delay is real, it's measurable, it has consequences. But from the photon's perspective, something very different happens. According to relativity time, dilation at the speed of light is infinite. For the photon, no time passes at all. The moment it leaves the sun's surface and the moment it strikes Earth, or your eye, or a solar panel, are the same instant. Zero time, no duration, no waiting. Think about what that means. The photon doesn't experience the journey. It doesn't feel 8 minutes passing. From its frame of reference, if we can imagine such a thing, the sun and Earth are in the same place touching, with no distance between them. Space itself contracts to zero length at light speed. The entire 93 million mile journey from the photon's point of view happens in a single eternal now. It exists outside of time, outside of duration, in a state we can barely comprehend. This is one of the deepest mysteries of the universe. Time and space are not absolute. They're relative, flexible, dependent on how fast you're moving. For us, bound by mass and moving slowly compared to light time, flows forward. Space has extension and journeys take time. But for light itself, the rules are different. Photons live in a timeless realm where departure and arrival are simultaneous, where distance has no meaning, where the entire history of the universe from the Big Bang to the present is collapsed into a single moment. Scientists suggest this is why light can be both a particle and a wave, why it behaves in ways that seem contradictory to our everyday experience. We try to understand it through concepts like time and position, but light doesn't inhabit those concepts the way we do. It simply is existing in all the places along its path, simultaneously from its own perspective, at least, even though we observe it, moving, traveling, taking time. Now let's follow our photon as it crosses that 93 million mile gap. The sun recedes behind it. The photon passes through the corona, the sun's outer atmosphere, a region of superheated plasma that extends millions of kilometers into space. Here, the temperature paradoxically rises, reaching over 1,000,000 degrees, Kelvin much hotter than the photosphere below. Scientists are still working to fully understand why the corona is so hot, though magnetic fields and shock waves are thought to play a role. But our photon, uncharged and massless, passes through without interacting, unaffected by the heat or the magnetic turbulence. As it travels farther from the sun, the photon enters the heliosphere, the vast bubble of charged particles, the solar wind that streams out from the sun in all directions. The solar wind is made of electrons, protons, and heavier ions traveling at speeds of several hundred kilometers per second. To us, that seems fast, but to our photon moving at the speed of light, the solar wind particles might as well be standing still. The photon overtakes them effortlessly, racing ahead, leaving them behind in its wake. At about 46 million kilometers from the sun, the photon crosses the orbit of Mercury, the innermost planet. If Mercury happened to be in the right position, the photon might strike its surface, absorbed by dark rock converted to heat. But space is vast, and the chances of hitting anything are vanishingly small. The photon continues undisturbed. At 108 million kilometers, it crosses the orbit of Venus. Then at 150 million kilometers, it reaches the orbit of Earth. If our photon is aimed correctly, if its trajectory happens to intersect with that small blue world spinning in the darkness, it will enter the atmosphere and begin the final stage of its journey. But if not, it will simply continue outward past Mars, past the asteroid belt, eventually leaving the solar system entirely traveling into interstellar space, where it may wander for millions or billions of years without encountering anything at all. Let's assume our photon is one of the lucky ones. It's heading straight for Earth. The planet looms ahead, a pale blue dot, suspended in the blackness, oceans and clouds and continents visible even from a distance. The photon, oblivious to the beauty, simply continues on its predetermined path. And then, about 8 minutes and 20 seconds after leaving the sun, it makes contact. Here's something most people don't realize. The light we see from the sun isn't instantaneous. It's old. Not ancient like the cosmic microwave background, but old enough that if something catastrophic happened to the sun right now, we wouldn't know for 8 minutes and 20 seconds. The sun could go dark, explode, disappear entirely, and we'd continue to see it shining, warming our planet, casting shadows, completely unaware of the disaster. Only when the last photons emitted before the event arrived would we see the change. For those 8 minutes, we'd be living in a past that no longer exists, illuminated by light from a star that might already be gone. This delay has profound implications. When we look at the sun, we're not seeing it as it is now. We're seeing it as it was 8 minutes ago. And the same principle applies to everything in the universe. When you look at the night sky, you're looking into the past. The light from Alpha Centauri, the nearest star system, takes about 4 years to reach us. The light from distant galaxies can take billions of years. Astronomy is by its nature a study of history, a science of observing things as they were, not as they are. But back to our photon. It has crossed the void. It has traveled from the sun to Earth in what we perceive as 8 minutes and 20 seconds, but what it experiences as no time at all. Now comes the most complex part of its journey. The photon is about to enter Earth's atmosphere, a thin shell of gas that extends about 100 kilometers above the surface. And in that thin shell, it will encounter more obstacles, more interactions, more chances to scatter and change direction than in all the millions of kilometers of empty space it just crossed. The atmosphere is dense compared to the vacuum of space. At sea level, it contains about 2.5 times 10 to the 19th particles per cubic centimeter. That's 25 quintillion, the number we mentioned earlier. And every single one of those particles, nitrogen, oxygen, argon, carbon dioxide, water vapor, is a potential obstacle for our photon. Some photons will be absorbed, some will be scattered, some will make it through to the surface, and some will be reflected back into space, never touching the ground at all. Research shows that about 30% of the sunlight that reaches Earth's atmosphere is reflected back into space by clouds, ice, and the atmosphere itself. Another 20% is absorbed by the atmosphere, warming the air, driving weather patterns, powering the water cycle. The remaining 50% makes it to the surface, where it warms the land and oceans, fuels photosynthesis, and allows us to see. Our photon, if it's part of that 50%, is about to complete its journey. But first, it must navigate the atmosphere's many layers, each with its own characteristics, its own hazards. Have you ever wondered why the sky is blue? It's because of our photon and millions like it, scattering through the atmosphere in a very specific way. But that's a story for the next part of this journey, as our traveler encounters air molecules, water droplets, and the complex interplay of light and matter that creates the colors we see every day. The void has been crossed, the destination is near, and what happens next will transform our photon one final time, preparing it for the moment when it finally, after billions of years of existence, becomes something more than light. It becomes vision, it becomes warmth, it becomes life itself. Imagine you're a photon that has traveled billions of years, crossed the void of space in 8 minutes. And now you're about to enter a maze of molecules where every collision changes your direction, your energy, your fate. The atmosphere seems thin from space, just a delicate blue halo around a rocky planet. But for light trying to pass through, it's a gauntlet of interactions that will determine whether you reach the ground as sunlight scatter into the sky as blue or reflect back into space, never to be seen at all. This is where color is born. Our photon strikes the upper atmosphere at an altitude of about 100 kilometers, traveling at the speed of light. The first thing it encounters is the thermosphere, a layer so sparse that air molecules are separated by relatively large distances. Here, the photon might pass through without hitting anything at all, slipping between oxygen and nitrogen molecules like threading a needle. But as it descends, the atmosphere grows denser, more molecules, more chances to interact, and with each kilometer downward, the probability of collision increases. At about 50 kilometers altitude in the mesosphere, our photon finally encounters its first obstacle. A molecule of nitrogen vibrating in place suddenly intercepts the photon's path. What happens next is called Rayleigh scattering, named after the British physicist Lord Rayleigh, who first described it mathematically in the 1870s. The photon doesn't bounce off the molecule like a ball hitting a wall. Instead, it's absorbed completely. The molecule takes in all the photon's energy, becomes excited, and then almost instantly re-emits a new photon, usually in a completely different direction. Here's the crucial part. Rayleigh scattering is wavelength dependent. Shorter wavelengths, blue and violet light, are scattered much more strongly than longer wavelengths like red and orange. Scientists have calculated that blue light with a wavelength of about 450 nanometers is scattered almost 10 times more efficiently than red light, which has a wavelength of about 700 nanometers. This is why the sky appears blue. When sunlight enters the atmosphere, the blue photons get scattered in all directions, filling the sky with blue light, while the red and orange photons mostly continue straight through. Our photon, let's say it's in the blue part of the spectrum, gets scattered. It was heading straight down toward the surface, but after colliding with that nitrogen molecule, it's now heading sideways or even upward. Then it hits another molecule, scattered again, then another, and another. Each collision sends it in a new random direction, creating a complex zigzag path through the atmosphere. Some photons like ours will be scattered so many times that they'll eventually head back out into space, never reaching the ground. Others will make their way down, arriving at the surface from a seemingly random direction, which is why shadows aren't completely black. Even in shade-scattered blue light from the sky provides illumination. This scattering effect creates the blue dome we see above us. But here's something beautiful. The exact shade of blue depends on how much atmosphere the light passes through. When you look straight up, you're looking through the least amount of air, and the sky appears a deeper, darker blue. When you look toward the horizon, the light passes through much more atmosphere, scattering multiple times, and the sky appears paler, almost white near the horizon. The same principle explains why the sky looks different at different altitudes. Astronauts in orbit see a much darker blue, almost black, because there's less atmosphere above them to scatter the light. Now, imagine it's late afternoon. The sun is low on the horizon. Our photon, if it managed to survive the journey through the atmosphere without being scattered away, has to pass through a much thicker layer of air to reach the surface. The path, length through the atmosphere, can be 20 or 30 times longer at sunset than at noon, and this makes all the difference. With so much more air to traverse, almost all the blue light gets scattered out of the direct beam. What remains are the longer wavelengths, the reds, oranges, and yellows. This is why sunsets are red. The blue light has been removed, scattered away into the sky, leaving only the warm colors to paint the horizon. Research shows that the intensity of sunset colors depends on what's in the atmosphere. Volcanic eruptions, for example, can inject tiny particles and sulfur dioxide into the stratosphere, creating spectacular red and purple sunsets for months or even years afterward. The eruption of Mount Pinatubo in the Philippines in 1991 produced some of the most vivid sunsets in recorded history, visible around the world, because the volcanic aerosols enhanced the scattering and absorption of sunlight. Even pollution, unfortunately, can intensify sunset colors, though at the cost of air quality and health. But let's return to our photon. It's survived the scattering gauntlet and is now descending through the troposphere, the lowest layer of the atmosphere where weather happens. Here, it encounters a new set of obstacles: water droplets, ice crystals, dust particles, each one larger than air molecules and each one capable of interacting with light in different ways. When a photon encounters a water droplet, something different happens. Instead of Rayleigh scattering, which works for particles much smaller than the wavelength of light, we get Mie scattering, named after the German physicist Gustav Mie. Mie scattering occurs when the scattering particle is comparable in size to the wavelength of light, and unlike Rayleigh scattering, it doesn't favor shorter wavelengths as strongly. All wavelengths are scattered more equally. This is why clouds appear white. The water droplets in clouds scatter all colors of light roughly equally. And when you mix all the colors together, you get white. Our photon might pass through a cloud, scattering from droplet to droplet, bouncing around inside the cloud like a pinball, before eventually escaping, either back toward space or down toward the ground. Dense clouds can reflect up to 90% of the sunlight that hits them, which is why overcast days are so much dimmer than sunny ones. The photons simply aren't making it through. If our photon is lucky enough to pass through a region with just a few water droplets, it might encounter another phenomenon called refraction. When light passes from one medium to another, say from air into water, it changes speed and direction. The photon slows down slightly in the denser medium, and if it enters at an angle, it bends. This bending is what creates rainbows. Sunlight enters a raindrop, refracts, reflects off the back of the droplet, refracts again as it exits, and in the process, the different wavelengths separate. Red light bends, least violet light bends most, and the result is a spectrum of colors arranged in a perfect arc across the sky. Scientists have calculated that the angle at which you see a rainbow, the angle between the incoming sunlight and your line of sight to the droplet, is always about 42 degrees for red light and about 40 degrees for violet light. This is why rainbows always appear in the same position relative to the sun, and why you can never walk to the end of a rainbow. It's not a physical object, it's an optical effect, a consequence of countless photons being refracted and reflected by millions of water droplets, each one contributing a tiny point of colored light that your eye and brain assemble into that beautiful arc. There's a common misconception that rainbows are rare or special. In reality, whenever you have sunlight and water droplets in the air, and you're standing in the right position with the sun behind you, there's a rainbow. You might not always notice it. It might be faint or partial. But the conditions for rainbows are created constantly every time it rains while the sun is shining. Some people have even created rainbows artificially using garden hoses, spraying water into the air on a sunny day, and standing in the right spot to see the colors appear. Our photon, if it passed through a raindrop, might have been part of a rainbow someone saw months or years ago, contributing one tiny point of red or blue or green light to that arc before continuing on its way. Or it might have missed the raindrops entirely, continuing its descent through clear air heading toward the surface. As the photon approaches the ground, it encounters one final layer of complexity. The boundary layer, the lowest few meters of the atmosphere, is turbulent, filled with swirling air currents heated by the sun-warmed ground. This turbulence causes the refractive index of the air to fluctuate rapidly, which makes the light passing through it shimmer and dance. This is what causes stars to twinkle. The starlight, traveling for years or centuries across space, arrives at Earth as a steady beam, but in the last few kilometers through our atmosphere, it gets bent and distorted by turbulent air, making the star appear to flicker and change positions slightly. It's also why astronomers build observatories on high mountains or launch telescopes into space. The less atmosphere you look through, the clearer and steadier the view. Our photon descending through this turbulent layer might wobble slightly in its path, but it's moving so fast that the effect is negligible. And then finally, after passing through 100 kilometers of atmosphere, after dodging molecules scattering through clouds, perhaps refracting through raindrops, it reaches the surface. It might strike a leaf, triggering photosynthesis. It might hit the ocean, warming the water. It might land on a solar panel converted to electricity. Or it might enter your eye. The journey through the atmosphere has been chaotic, unpredictable, full of chances to be scattered away or absorbed. But our photon made it. And in making it, it participated in creating all the phenomena we associate with daylight. The blue sky, the red sunset, the white clouds, the rainbow's arc. Every one of these is the result of countless photons interacting with air and water in ways that Lord Rayleigh and Gustav Mee and countless other scientists worked so hard to understand. Think about it. Every time you look up at a blue sky, you're seeing light that has been scattered by molecules so small you could fit billions of them on the head of a pin. Every sunset is a demonstration of wavelength-dependent, scattering a natural spectroscope painting the horizon with the colors that survived the longest path through the air. Every rainbow is a lesson in refraction and reflection angles and wavelengths, water and light, conspiring to create beauty. The atmosphere isn't just a protective blanket. It's an optical instrument, a filter, a prism, a canvas, where light paints pictures that change every moment of every day. And our photon, having navigated this complex maze, having survived scattering and absorption and refraction, is now poised to complete the final leg of its journey, from the surface to the eye, from light to vision, from physics to perception. And that transformation, that moment when a photon becomes an experience, is perhaps the most miraculous part of this entire 13.8 billion year odyssey. A photon crosses 13.8 billion years, survives. A star's interior navigates an atmosphere, and then in the final millionths of a second, it does something no amount of distance or time could prepare it for. It stops being light and becomes sight. It enters the human eye, triggers a molecular cascade so precise and so fast that scientists are still unraveling its mysteries, and transforms from a particle of physics into an experience of consciousness. This is the moment everything changes. Our photon has reached the surface. It bounces off a flower petal, a leaf, maybe the page of a book, and changes direction one last time. Now it's heading toward you, toward your eye, carrying information about color and brightness reflected from that surface just microseconds ago. The distance from the object to your eye might be only a few feet, but for our photon, it's the final approach after an incomprehensible journey. And what waits ahead is perhaps the most sophisticated optical instrument in the natural world. The human eye is not a camera, though the comparison is often made. It's something far more complex, far more dynamic. It doesn't simply record light. It interprets it, adjusts to, it focuses it, and converts it into electrical signals that your brain can understand. The eye evolved over hundreds of millions of years, refined through countless generations, shaped by the need to detect predators, find food, recognize faces, navigate terrain. And all of it depends on one thing: the ability to capture photons and turn them into meaning. Our photon approaches the eye. The first barrier it encounters is the cornea, the clear dome at the front of the eye. The cornea is made of precisely arranged collagen fibers organized in a way that makes it transparent. Most tissues in the body scatter light, which is why you can't see through your hand or your arm. But the cornea's fibers are spaced at distances smaller than the wavelength of visible light, and they're aligned in a regular pattern. This allows light to pass through without scattering, maintaining clarity. Research shows that the cornea provides about 2/3 of the eye's total focusing power, bending incoming light rays inward, beginning the process of creating a sharp image. As our photon passes through the cornea, it refracts slightly, bending toward the center of the eye. Then it enters the anterior chamber, a small space filled with a clear fluid called aqueous humor. This fluid nourishes the cornea and the lens, both of which have no blood vessels because blood vessels would block light. The photon crosses this chamber in a tiny fraction of a second, barely slowing down. Next comes the pupil, the black circle at the center of the iris. The pupil isn't a physical structure. It's an opening, a hole that allows light to pass into the deeper parts of the eye. The iris, the colored part surrounding the pupil, is a muscle that can expand or contract, changing the size of the pupil. In bright light, the pupil constricts to about 2 millimeters in diameter, limiting the amount of light entering and protecting the sensitive retina at the back of the eye. In darkness, it dilates to about 8 millimeters, allowing more light in to maximize vision. This adjustment happens automatically controlled by the autonomic nervous system, and it takes only a few seconds. Our photon passes through the pupil. If the pupil had been constricted, the photon might have been blocked, hitting the iris instead and being absorbed. But let's say the lighting is moderate, the pupil is open, and the photon makes it through. Now it encounters the lens, a flexible, transparent structure suspended behind the pupil by tiny fibers called zonules. The lens provides the final focusing adjustment, fine-tuning the path of the light to create a sharp image on the retina. Unlike the cornea, which has a fixed shape, the lens can change its curvature, becoming thicker to focus on nearby objects and thinner to focus on distant ones. This process, called accommodation, is controlled by the ciliary muscles around the lens. When you look at something close, like the words on this screen, your ciliary muscles contract, allowing the lens to bulge. When you look at something far away, like the horizon, the muscles relax and the lens flattens. This happens automatically dozens of times a minute, so smoothly that you don't even notice it. But as people age, the lens becomes stiffer, less able to change shape, which is why many people need reading glasses as they get older. The flexibility is lost. The focusing power diminishes. Our photon passes through the lens, refracting one more time, and enters the vitreous humor, a gel-like substance that fills the main cavity of the eye. The vitreous is clear, transparent, and it helps maintain the eye's shape. It also slows the photon down very slightly because the refractive index of the vitreous is higher than that of air. But the photon is still moving at incredible speed, and in less than a nanosecond, it crosses the vitreous and reaches its final destination, the retina. The retina is where light becomes biology. It's a thin layer of tissue lining the back of the eye, packed with specialized cells called photoreceptors. There are two types of photoreceptors, rods and cones. Rods are incredibly sensitive, able to detect even a single photon under the right conditions, and they're responsible for vision in low light. But they don't detect color. Cones, on the other hand, are less sensitive but can distinguish different wavelengths, giving us color vision. Humans have 3 types of cones, each sensitive to a different range of wavelengths. Short wavelength cones detect blue light. Medium wavelength cones detect green. Long wavelength cones detect red. By comparing the signals from these 3 types, your brain can perceive millions of different colors. Our photon, let's say it's green light, with a wavelength of about 550 nanometers, strikes a cone cell. And here's where the magic happens. The photon is absorbed by a molecule called a photopigment, specifically a protein called opsin, bound to a small light-sensitive molecule called retinal. When the photon hits retinal, it causes the molecule to change shape, flipping from a bent configuration to a straight one. This change takes only a few trillionths of a second, making it one of the fastest molecular reactions in biology. That tiny shape change triggers a cascade. The altered retinal activates the opsin protein, which in turn activates a molecule called transducin. Transducin activates an enzyme called phosphodiesterase. Phosphodiesterase breaks down a molecule called cyclic GMP. And when cyclic GMP levels drop, ion channels in the cell membrane close. Sodium ions can no longer enter the cell. The cell's voltage changes. It hyperpolarizes. And this change in voltage, this shift in electrical potential, is the signal. This is the moment when a photon, a massless particle of light, becomes a neural impulse, an electrical message that can be sent to the brain. Scientists estimate that this entire cascade from photon absorption to electrical signal takes less than a millisecond, and it's astonishingly sensitive. Research shows that rod cells can respond to a single photon, just one. If you're in a completely dark room and a single photon enters your eye and happens to hit a rod cell, that cell will generate a signal. Your brain might not consciously register it because it takes several photons hitting several cells in a short time to cross the threshold of awareness. But the machinery is there ready to detect the faintest glimmer of light. But our photon hit a cone cell, not a rod, and now the signal is traveling. The cone cell connects to a bipolar cell, which connects to a ganglion cell, which sends a long fiber and axon back through the retina toward the optic nerve. The optic nerve is a bundle of about 1 million axons, all carrying signals from different parts of the retina, all converging at the back of the eye and exiting through a small opening called the optic disc. Interestingly, the optic disc has no photoreceptors because the nerve fibers have to pass through. This creates a blind spot in your vision, a small area where you can't see anything. But your brain fills it in, inventing visual information based on the surrounding context, so you never notice it's there. The signal from our photon, now an electrical impulse, travels along the optic nerve toward the brain. The nerve crosses underneath the brain at a structure called the optic chiasm, where some of the fibers from each eye cross to the opposite side. This crossing ensures that information from the left side of your visual field, seen by both eyes, goes to the right side of your brain, and vice versa. It's one of the strange quirks of how our visual system evolved. From the optic chiasm, the signal continues to a part of the brain called the lateral geniculate nucleus, a relay station in the thalamus. Here, the signal is processed, filtered, adjusted, and then it's sent to the primary visual cortex located at the very back of the brain in the occipital lobe. This is where conscious vision begins, where the electrical signals are transformed into an image, a perception, a visual experience. But here's something profound. The photon itself is gone. It was absorbed by the retinal molecule. Its energy was converted into a molecular shape change. The photon no longer exists as a particle of light. It has been destroyed, annihilated, transformed into something else entirely. And yet, in being destroyed, it created something new: information, a signal, an experience. The photon's 13.8 billion year journey has ended, but its legacy continues as a tiny part of your visual awareness. What's remarkable is how much processing happens before you're even aware of seeing anything. The retina doesn't just detect light, it analyzes it. Research shows that different types of ganglion cells respond to different features of the visual scene. Some detect edges, some detect motion, some respond to changes in brightness. The retina is performing sophisticated computations, extracting information, filtering noise before the signals even reach the brain. Vision isn't passive, it's active, interpretive, constructed. And here's another layer of complexity. Color doesn't exist in the world, not really. What exists are photons with different wavelengths. Our photon had a wavelength of about 550 nanometers. That's a physical property measurable objective. But green, the color you perceive, is a creation of your brain. Your brain takes the signals from your 3 types of cone cells, compares them, and generates the sensation of greenness. Someone else might experience that same wavelength slightly differently, perceiving a slightly different shade. And some people, those with color blindness, might not distinguish it from other wavelengths at all because they're missing 1 or more types of cone cells. This raises a beautiful question. Do we all see the same colors? Does the green you see match the green I see? We can never know for certain because we can't step inside each other's minds and compare experiences directly. We use the same words to describe colors, so we assume we're seeing the same thing. But the actual subjective experience, the qualia of greenness, might be subtly or even dramatically different from person to person. It's one of the enduring mysteries of consciousness. Our photon's energy, now dispersed through the neural cascade, has contributed to a pattern of activity in your visual cortex. That pattern is being integrated with signals from millions of other photons, all hitting the retina at slightly different times and places, all creating their own cascades, all contributing to the overall image. And your brain is assembling those signals into a coherent picture of the world. A flower, a face, a sunset, whatever you happen to be looking at in that moment. But the story doesn't end in the visual cortex. The signals spread further into areas of the brain responsible for memory, emotion, recognition. If the image is of something familiar, a loved one's face, a childhood home, those associations are activated, memories are triggered, emotions arise. What started as a photon, a massless particle born in the Big Bang or created in a star, has now become part of your inner life, woven into the fabric of your consciousness, indistinguishable from you. Think about that. Every time you see, you're experiencing the endpoint of countless photons' journeys. Some traveled for 8 minutes from the sun, others for years from distant stars. A few, like the ones from the cosmic microwave background, have been traveling for over 13 billion years. And all of them, when they finally reach your eye, undergo the same transformation, from light to chemistry, from chemistry to electricity, from electricity to perception, from perception to thought, feeling, memory. The eye is the bridge between the physical universe and the realm of subjective experience. It's the place where objective reality, photons and wavelengths and electromagnetic radiation become subjective awareness, colors and shapes and beauty. And that transformation, that translation from the language of physics to the language of consciousness, is still one of the deepest mysteries in science. Our photon is gone, but it's also eternal. Its energy lives on in your brain, contributing to your perception, your understanding, your experience of being alive. And as your brain processes that information, as it integrates it with memories and emotions, as it constructs your ongoing experience of the world, the photon's journey reaches its ultimate destination. Not just your eye, not just your brain, but you, the conscious being who sees who, knows who, wonders about photons and journeys and the nature of light itself. The photon has become part of your story now, and in becoming so, it completes a circle that began at the birth of the universe. From the Big Bang to your eye, from light to life, from the cosmos to consciousness. And every single moment you see, every glance and gaze and glimpse repeats that ancient miracle, turning starlight into sight over and over again. But the question remains, what happens to that information once it's in your brain? How does a pattern of electrical signals become a memory, a thought, a part of who you are? That transformation from vision to meaning is where our journey leads us now. What if every memory you have is just light that stayed? What if the sunset you remember from childhood, the face of someone you loved, the color of your first car, all of it is really just patterns of ancient photons transformed into chemistry, woven into the fabric of who you are? A photon travels billions of years to reach your eye, triggers a cascade of signals in your brain, and then something miraculous happens. It stops being temporary and becomes permanent. It becomes you. The electrical signal from our photon has reached your visual cortex. It's been processed, filtered, compared with signals from millions of other photons arriving at the same time. Your brain has constructed an image, a perception, a momentary experience of seeing something. But in most cases, that experience fades almost immediately. You see 1,000 things every minute, and most of them disappear from awareness within seconds. The brain can't hold on to everything. It has to choose what matters, what's worth keeping, what deserves to become a memory. So, how does the brain decide? How does a fleeting pattern of neural activity generated by a photon that no longer exists become something that can last a lifetime? The answer lies in a small curved structure deep in your brain called the hippocampus. Named after the Greek word for seahorse, because of its shape, the hippocampus is the gateway to long-term memory. It's where temporary experiences are evaluated and coded. and if they pass certain thresholds of importance or emotional significance transferred into more permanent storage. Research shows that the hippocampus doesn't store memories itself. Instead, it coordinates the storage process across different regions of the cortex. When you see something, the visual information is initially held in the visual cortex. But if the hippocampus determines that this information is worth keeping, it orchestrates a process called consolidation, where the neural patterns are gradually transferred to other areas of the brain, distributed across networks that can hold them indefinitely. The memory of what you saw becomes encoded in the connections between neurons in the strength of synapses in patterns that can be reactivated later when you remember. But here's the fascinating part. Memories aren't stored like files on a computer, where you save a perfect copy that never changes. Every time you remember something, you're reconstructing it, rebuilding it from fragments, and in the process, you might change it slightly. Scientists call this reconsolidation. Each time a memory is recalled, it becomes temporarily unstable, vulnerable to modification before being stored again. This means that your memory of seeing a particular sunset triggered by photons from the sun hitting your retina years ago isn't a perfect recording. It's a living thing shaped by every time you've thought about it since. Think about a significant visual memory from your past. Maybe the first time you saw the ocean, or a loved one's face at a meaningful moment, or the view from a place you once called home. That memory feels vivid, real, like you're seeing it again. But neuroscientists suggest that what you're experiencing is a reconstruction, a pattern of neural activity similar to the original, but not identical. Some details have been lost, others have been enhanced. Emotions have been added or subtracted. The memory has been influenced by everything that came after every related experience, every story you told about it, every time you consciously or unconsciously retrieved it. The visual cortex plays a crucial role in this. When you remember seeing something, many of the same areas that were active when you originally saw it become active again. It's as if your brain is replaying the visual experience using the same neural machinery. Brain imaging studies using fMRI have shown that when people remember visual scenes, their visual cortex lights up in patterns that partially match the original perception. The memory isn't just stored as abstract information. It's stored in a form that can recreate the experience of seeing at least partially. But what determines which photon-triggered experiences become memories and which fade away? One major factor is attention. If you're paying attention to something when you see it, if you're focused and engaged, the hippocampus is more likely to encode it. Attention acts like a spotlight, highlighting certain neural patterns and marking them as important. Another factor is emotion. Experiences that trigger strong emotional responses, whether positive or negative, are more likely to be remembered. The amygdala, a brain structure involved in processing emotions, communicates directly with the hippocampus. And when the amygdala signals that something is emotionally significant, the hippocampus prioritizes it for storage. There's also repetition. If you see something once, it might not stick. But if you see it multiple times, or if you consciously rehearse the memory, thinking about it repeatedly, the neural connections strengthen. Scientists call this synaptic plasticity, the brain's ability to change the strength of connections between neurons based on use. When a particular pattern of neural activity is repeated, the synapses involved become more efficient, making it easier to reactivate that pattern in the future. This is why we remember faces we see every day, but forget faces we glimpsed once in a crowd. Repetition matters. Our photon absorbed in your eye triggered a cascade that reached your visual cortex and generated a brief pattern of activity. If that moment was unremarkable, if you were distracted, if nothing about it stood out emotionally, the pattern probably faded within seconds. The photon's information was processed, used to guide your immediate behavior, and then discarded. But if the moment was significant, if you were looking at something that mattered, the hippocampus took note. The pattern was marked for consolidation. And over the following hours and days, while you slept and while you went about your life, Your brain gradually transferred that information into long-term storage. Sleep is crucial for this process. During sleep, particularly during deep non-REM sleep and REM sleep, the hippocampus replays the day's experiences, reactivating neural patterns in a compressed, accelerated form. Research shows that these replays can happen at speeds many times faster than the original experience, like watching a recording on fast forward. As the hippocampus replays the patterns, the cortex gradually takes over, embedding the information into its networks. By morning, the memory has been moved, distributed, stabilized. What was once a fragile temporary pattern has become part of the brain's permanent architecture. But here's something beautiful and slightly unsettling. The photon that started this process is long gone. It was destroyed the moment it was absorbed by the retinal molecule in your eye. Its energy was converted, passed along, transformed into electrical signals, into molecular changes, into strengthened synapses. And yet, in a sense, the photon lives on. Its legacy is encoded in your brain, in the pattern it helped create, in the memory it contributed to. You can't point to any single molecule or cell and say, that's where the photon is. The information is distributed, smeared across thousands or millions of synaptic connections. But it's there, preserved in a form that allows you to remember, to recall, to experience again, something that happened once and is now past. This raises a profound question about identity. If your memories are made of light transformed and stored as neural patterns, and if those patterns change every time you access them, what does that mean for who you are? Philosophers and neuroscientists have long debated the relationship between memory and identity. Are you the sum of your memories? If your memories change, do you change? If you remember something differently than it actually happened, which version is the real you? There's a famous case in neuroscience involving a patient known as HM, Henry Molaison, who had parts of his hippocampus removed in the 1950s to treat severe epilepsy. After the surgery, he could no longer form new long-term memories. He could hold information in his mind for a few minutes, but as soon as he was distracted, it vanished. He lived in a perpetual present, unable to remember what he'd seen, whom he'd met, or what he'd done just hours earlier. His case revealed how essential the hippocampus is for memory formation. Without it, visual experiences, photons striking the retina and generating neural activity, couldn't become lasting memories. They remain trapped in the moment, destined to fade. But HM retained his old memories, the ones formed before the surgery. He could remember his childhood, his early adulthood, things he'd seen decades earlier. This showed that long-term memories, once consolidated, don't depend on the hippocampus. They're stored elsewhere, distributed across the cortex, resilient and enduring. The photons that reached his eyes in his youth, that triggered experiences he encoded before his surgery, remained accessible to him. Even as new photons, new experiences slipped away unrecorded. Your brain is doing this constantly, evaluating, encoding, consolidating. Every moment you see something, photons are triggering cascades, generating patterns, and your brain is deciding what to keep and what to let go. Most of it is let go. You don't remember every glance at the floor, every peripheral flicker of movement, every mundane detail of your visual field. But the important moments, the emotionally significant ones, the ones you attend to and rehearse, those are preserved. Those photons, in a sense, become part of you. And here's another layer. Memories aren't just passive records. They influence how you perceive new experiences. When a photon enters your eye now, your brain doesn't just process it in isolation. It compares it to stored patterns, to memories of similar things you've seen before. This is how you recognize objects, faces, places. Recognition is the brain matching current input to past input, finding similarities, making connections. The photons that shaped your memories are now shaping how you see the present. Scientists suggest that this is why nostalgia is so powerful. When you see something that resembles a memory, when the current pattern of photons hitting your retina is similar to a pattern from your past, the old memory is reactivated. and with it come the emotions, the associations, the context. A certain quality of afternoon light might remind you of summers from childhood. A particular shade of blue might evoke a place you once visited. The smell of rain, though not itself photons, often accompanies visual memories, creating multisensory experiences that feel vivid and immediate. The photons that created those original experiences are influencing your experience now, even though they're long gone. There's a concept in neuroscience called priming, where exposure to one stimulus influences your response to a later stimulus. If you see a yellow flower, you might be slightly more likely to notice other yellow things afterward, because the neural pathways for processing yellow have been recently activated. The photons from the flower have primed your brain, making it temporarily more sensitive to similar patterns. Memory works similarly on a longer time scale. The photons that created your memories have primed your entire perceptual system, shaping what you notice, what you value, what catches your eye. And then there's the question of false memories. Sometimes your brain creates memories of things you never actually saw, stitching together fragments from different experiences, or filling in gaps with plausible details. In experiments, researchers have successfully implanted false memories in participants, convincing them they remember events that never happened, including vivid visual details. This shows how reconstructive memory is, how vulnerable to suggestion and imagination. The photons that actually entered your eyes might be only a small part of what you remember. The rest is fabrication invention. Your brain's best guess at what probably happened. Does this make memory unreliable? In some ways, yes. Eyewitness testimony, once considered highly credible, is now known to be fallible. People remember details, incorrectly confuse sources, incorporate information they learned later into their original memory. But in another way, this flexibility is a feature, not a bug. Memory isn't meant to be a perfect archive. It's meant to be useful to help you navigate the present and predict the future. By reconstructing memories each time you recall them, your brain can update them with new information, keep them relevant, adapt them to your current understanding of the world. Our photon absorbed in your eye, perhaps years ago, contributed to a memory that's now woven into the vast network of who you are. That memory might have changed since it was first formed. It might have merged with other memories, been embellished with details from stories you've told, faded in some areas and sharpened in others. But is there a trace of ancient light, preserved in the connections between your neurons, ready to be recalled whenever something in your present experience triggers the right pattern of activation? And every time you remember, you're bringing that photon's journey back to life. Not the photon itself that's gone transformed into heat and chemical energy within moments of being absorbed, but the information it carried, the pattern it helped create lives on. It's a strange kind of immortality, a photon born in the Big Bang or created in a star or emitted by the sun, travels across space and time, enters your eye, and becomes part of your mind, your identity, your history. It becomes a memory. You can revisit a moment. You can relive a piece of light that stayed. How many photons are stored in your brain right now, transformed into memories? How many moments of seeing how many faces and places and scenes have been encoded in your neural networks waiting to be remembered? The number is staggering beyond counting. Every visual memory you have represents millions or billions of photons that struck your retina, each one contributing a tiny fragment of information, each one now preserved in a form that allows you to say, I remember, I was there, I saw that. And in saying that, you're honoring the journey those photons took to reach you, the vast distance and time they crossed, the transformations they underwent, all leading to this. A memory, a moment, a part of you. But the story of our photon's journey isn't finished yet. Because what happens when that memory, that preserved pattern of light, becomes more than just stored information? What happens when it shapes your thoughts, your decisions, your understanding of yourself and the universe? That final transformation from memory to meaning is where the photon's 13.8 billion year odyssey reaches its deepest and most mysterious conclusion. 13.8 billion years. That's how long it took for a single photon to complete its journey from the first moments of creation to this moment right here, right now, resting gently in your thoughts. From the fire of the Big Bang, through the darkness of cosmic dawn, from the heart of a star to the 8-minute crossing of space through the atmosphere's dance of scattering and color into your eye, where it triggered a cascade so precise it borders on miraculous, and finally into your brain, where it became memory. Meaning part of the story you tell yourself about who you are. But what does it all mean? What is the ultimate destination of a photon's journey? Perhaps the answer is simply this: wonder. The photon traveled all that distance all that time so that you could pause for a moment and marvel at the fact that you can see it all, that you can perceive color, recognize faces, navigate the world, remember sunsets, and understand, even in a small way, the physics that makes it all possible. Every photon that enters your eye is a messenger from the past, carrying information across the void, connecting you to stars that died before Earth was born, to moments that happened billions of years ago, to a universe so vast and so ancient that it almost defies comprehension. Scientists estimate that about 100 trillion photons enter your eyes every second during daylight. 100 trillion, each one with its own journey, its own history, its own path through space and time. Some are fresh, just 8 minutes old, warm from the sun's surface. Others are ancient, traveling for thousands or millions of years from distant stars. And a tiny few, the ones from the cosmic microwave background, are more than 13 billion years old, having witnessed the entire history of the universe from a time when galaxies didn't exist. You are constantly, every moment of your waking life, bathed in this river of light, this flood of ancient and modern photons converging on you from every direction. And what do you do with all this light? You use it to see, yes, to navigate, to read, to recognize the people you love, but you also use it to understand. The same processes that allow you to see a flower or a face also allow you to study the cosmos, to decode the messages hidden in starlight, to learn about the composition of distant suns, the motion of galaxies, the age and fate of the universe itself. Every field of astronomy, every discovery about the nature of reality comes from analyzing light. Photons are our only direct connection to the universe beyond our immediate reach. We can't touch distant stars. We can't travel to other galaxies, not yet. Maybe not ever. But we can collect their light, study its properties, decode its secrets. When astronomers analyze the spectrum of light from a distant star, they're seeing photons that left that star decades, centuries, or millennia ago. The light carries information about the star's temperature, its composition, its motion. If the spectral lines are shifted toward the red end of the spectrum, the star is moving away from us. If they're shifted toward the blue, it's moving closer. This simple observation that light changes wavelength depending on the motion of its source allowed scientists to discover that the universe is expanding, that galaxies are rushing apart, that everything began in a single moment of incredible heat and density. The Big Bang Theory itself is built on observations of light, on the study of photons that traveled billions of years to reach our telescopes. The cosmic microwave background, which we've mentioned throughout this journey, is perhaps the most important light source in all of cosmology. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate persistent noise from a radio antenna. The CMB is the smoking gun evidence for the Big Bang. It's the oldest light we can see, the afterglow of the moment when the universe became transparent, and it's almost perfectly uniform in all directions, with only tiny fluctuations that reveal the seeds of galaxies. By studying these fluctuations in exquisite detail, scientists have been able to determine the age of the universe, the density of matter and energy, the rate of expansion, even the geometry of space itself, all from analyzing light. And here's the beautiful irony. The photons that carry this information, the ones that allow us to understand the universe, are the same photons that allow us to see our immediate surroundings. There's no fundamental difference between the photon that shows you a flower and the photon that tells astronomers about the composition of a star 10,000 light years away. They're both just electromagnetic radiation, traveling at the speed of light, carrying energy and information from one place to another. The only difference is how we choose to use them. Our photon, the one we've been following through this entire story, has completed its transformation. It began as pure energy in the chaos of the Big Bang, trapped and scattered through the opaque early universe. It was freed during recombination and drifted through the dark ages, witnessing the birth of the first stars. Perhaps it was absorbed and re-emitted countless times in the interior of a massive star, contributing to the nuclear fusion that powers the cosmos. It crossed the void of space, experiencing no time at all from its own perspective, and entered Earth's atmosphere, where it scattered through air and water, creating the colors we associate with sky and sunset. It penetrated your eye, triggered a molecular cascade in your retina, became an electrical signal in your brain, and was encoded as memory, as meaning, as part of your understanding of the world. And now, as you think about this photon, as you consider its journey, you're activating neural patterns that were shaped by countless other photons, memories of things you've seen, knowledge you've acquired, emotions you've felt. The boundaries blur. Where does the photon end and you begin? The information it carried has been integrated into your mind so completely that it's no longer separate. It's you, your thoughts, your perceptions, your sense of self, all of it built from light, transformed and preserved in the architecture of your brain. There's a concept in physics called the light cone, the set of all events in space-time that can be influenced by a single point. If you imagine a photon being emitted at a specific place and time, its light cone includes everything that photon could potentially reach in the future. Our photon's light cone extended across 13.8 billion years, across billions of light years of space, and ended here in your mind. But the influence doesn't stop. Because now you know about this photon's journey, you've thought about it, been moved by it perhaps. And that knowledge might change how you see the world. You might look at sunlight differently, with a deeper appreciation for the journey it took to reach you. You might glance at the night sky and think about the ancient photons arriving from distant stars, time travelers carrying messages from the past. The photon's light cone, in a metaphorical sense, continues through you, affecting your thoughts, your actions, the stories you tell. Think about what this means on a human scale. Every time you see someone's face, you're receiving photons that reflected off their skin just nanoseconds ago. Those photons enter your eye, create a pattern in your visual cortex, and allow you to recognize them, to read their expression, to feel connection. The light bouncing between you and another person is the medium of recognition, of communication, of love. When you look into someone's eyes and feel understood, what's really happening is that photons are carrying information back and forth, reflected light, creating a feedback loop of mutual perception. You see them seeing you, they see you seeing them. And in that exchange of light, something profound occurs. Connection, presence, the shared experience of being alive at the same moment in time. Research in psychology shows that eye contact increases feelings of connection and empathy. When two people look at each other, their neural patterns begin to synchronize, mirroring each other's emotional states. Some of this happens through other cues, facial expressions, and body language, but much of it is mediated by light, by the photons that allow you to see subtle changes in pupil size, the crinkle around the eyes that signals a genuine smile, the slight furrowing of the brow that indicates concern. Light is the medium of empathy, the carrier of emotional information, the bridge between isolated minds. And on a larger scale, light is what allows humanity to function as a collective. Every written word, every image, every screen. You look at all of it depends on photons carrying information to your eyes. The accumulated knowledge of civilization, Everything we've learned and recorded is transmitted primarily through light. Books are read by reflected photons. Screens emit photons directly. Fiber optic cables use photons to carry data at incredible speeds, connecting billions of people across the planet in real time. The information age is really the photon age, an era where light has become the primary medium of communication, education, and culture. But let's return to the personal, to you sitting here perhaps in a quiet room listening to this story. Right now, photons are landing on your skin, warming you slightly, providing a fraction of the energy that keeps you alive. If you're near a window, sunlight is entering, illuminating the space, allowing you to see. Each photon is only 8 minutes old, fresh from the sun, but carrying energy that originated in fusion reactions deep in the solar core reactions that might have started 100,000 years ago. You are quite literally warmed by ancient light, sustained by photons that have been traveling longer than human civilization has existed. And if you step outside on a clear night, you can see photons from stars hundreds or thousands of light years away. The light from Betelgeuse, one of the brightest stars in the sky, takes about 650 years to reach Earth. When you look at Betelgeuse tonight, you're seeing it as it was in the 1300s during the Middle Ages, before the Renaissance, before the discovery of the Americas. The photon entering your eye right now left that star when humans were living in a completely different world, and it's been traveling ever since, crossing the void waiting to be seen. And Betelgeuse is relatively close. The Andromeda Galaxy, visible as a faint smudge in the night sky, is about 2.5 million light-years away. The photons you see from Andromeda left when early humans were just beginning to walk upright on the African savanna. They've been traveling since before our species existed, and they arrive now tonight, completing a journey that spans almost the entire history of humanity. Do you ever look at the stars and feel small? Many people do. The distances are so vast, the timescales so immense, that it's easy to feel insignificant. But here's another way to think about it. Those photons traveling for millions of years, crossing unimaginable distances, ended their journey in your eye. Of all the places they could have gone, of all the possible paths through the universe they found you, they entered your pupil, struck your retina, became part of your visual experience, your memory, your understanding. In that sense, you're not small. You're a destination, a gathering point for ancient light, a place where the universe becomes aware of itself. Carl Sagan famously said that we are made of star stuff, and it's true. The atoms in your body, the carbon, oxygen, nitrogen, iron, all of it was forged in the cores of stars that exploded billions of years ago, scattering their contents into space, where they eventually coalesced into new stars, planets, and you. But it's also true that you are made of light. The energy that powers your cells, that allows you to think and move and see, comes from the sun, from photons absorbed by plants through photosynthesis, then passed up the food chain to you. You are, in a very real sense, a structure built and maintained by light, a temporary pattern of matter, organized by the flow of photons from the sun. Without light, there would be no life, no consciousness, no you. And so, we come to the end of this journey, though it's not really an end at all. The photon we followed is gone, absorbed, and transformed, but its legacy remains. In your memory of this story, in your understanding of light and time, and the vast cosmos we inhabit, in the slight shift in how you perceive the world around you. Every sunset will mean a little more. Every star will carry a little more wonder. Every time you see, you'll remember, perhaps, that you're experiencing the endpoint of countless ancient journeys, photons arriving from near and far, from the past and the present, all converging to create this moment, this experience, this now. The universe is 13.8 billion years old. It began in fire, expanded into darkness, ignited with stars, and slowly, patiently over eons, created the conditions for planets, for life, for consciousness, for you. And the light from that beginning is still arriving, still traveling, still carrying messages from the edge of space and time. You are not separate from the universe. You are part of it, woven into it, made of the same stuff, shaped by the same forces, illuminated by the same light. So, the next time you step outside and feel the sun on your face, pause. Close your eyes, feel the warmth, and know that you're being touched by photons that traveled 8 minutes across 93 million miles of space to reach you. Photons that began their journey in the heart of a star. Photons that will soon be absorbed by your skin, converted to heat, to chemical energy, to the processes that keep you alive. You are held by light. Always. Every moment. And in being held, you become part of a story that began before anything existed and continues still, a story of energy and matter, of darkness and illumination, of journeys so long they defy comprehension and arrivals so precise they border on miraculous. Thank you for traveling with me through this story, through 13.8 billion years of light and time, from the Big Bang to this breath, this heartbeat, this moment of quiet wonder. The photon's journey has ended, but yours continues. And perhaps knowing what you know now, the world will seem a little brighter, a little more connected, a little more filled with ancient light. Sleep well, dream gently, and when you wake, the sun will rise again, and new photons will begin their 8-minute journey to you, carrying warmth, carrying life, carrying the endless story of the universe, becoming aware of itself through you. Until we meet again in the next quiet exploration. Rest easy knowing you are never alone in this darkness. You are held always in the gentle embrace of starlight. Good night.